Hi, this video is going to help with section 12.6 on what a vector is. So let's go over the definition of a vector. A vector has both magnitude and direction. You often use an arrow to represent a vector. So it's just an arrow with magnitude and direction. So magnitude happens to be the length of that arrow, where the initial point is the first point and the terminal point is the tip of the arrow. So this is a vector, V, and R is your terminal or first point, initial point, and then the terminal point is S, and the magnitude would be how long it is. Okay, so a vector is just an arrow. We have standard position of a vector. So let's look at what that kind of looks like. Standard position has the initial point of 0, 0. Okay, and is determined by the terminal point AB. So the magnitude would be of V would be the square root of A squared plus B squared. So let's look at component form and what all this means. Okay, so we're saying if that terminal point, that tip of that arrow, and if the is at AB and this one R is at 0, 0, it's in standard position. So that's typically what we deal with, standard position. Not always. In component form, we use these little, it looks like a parenthesis, but it's not. It's like a square arrow. So in Math Excel, you got to click on the tools button where they have like the square roots and the different symbols, and you have to look for this symbol. And we'll go A, B for our matrix form. And what you're really giving is that endpoint if it's in standard form, right? A is how far over, B is how far up. We also can write the vector in matrix form with A over B. Okay, so component form. So let's draw one. What if I had a vector? Oops. I'm looking at my original question 1 and I'm not ready to teach that yet. What if I had a vector that says 1, 4 in standard position? What is that vector going to look like? Well, it's going to be standard position means it starts at 0, 0. So you're here, right, for your endpoint, 0, 0. And then you're over 1, up 4. And that is going to be your AB or your terminal point. So your vector would look like that in standard position with the 1, 4. What if it wasn't in standard position? What if you want to write it in component form? That's with the little arrows. It looks like this. This is component form. Hold on just a sec. Let me draw it. So what if the vector starts out at 1, 2, and the vector ends at 8? So 1, 2, 3, 4, 5, 6, 7, 8, and 5. 1, 2, 3, 4, 5. 8, 5 is about there. What if this is my vector and I want to write it in component form? So I'm going to write it in component form. Now we know it's not in standard position. So how far away from standard position are we? That's what you want to look at. Well, instead of being at 0, 0, you're at 1, 2. So for the x value from 0, 0 to 1, you have moved 1 over. Or think of it as if I take the 1, 2, so we're going to think of it like this. I have the point 1, 2. How can I get to 0, 0 from this point? What would I do to the x value? Well, I would take that x value and subtract 1 because that's going to get me to 0, 0 if I subtracted that 1. What would I do to the y value is I would subtract 2, and that would get me to the standard 0, 0 starting point. So that's how far off we are. So what we're going to do is we're going to take this point, which was 8, 5, and we're going to subtract 1 and subtract 2, and then we would have it in component form, and that would show us what movement we've done. So we're going to subtract 1 from the 8, so 8 minus 1, and we're going to take the 5 and minus 2, and that is going to give me 7, 3. That is going to be our component form, 7, comma 3, with our little symbols for a vector. So you can take a vector that's not in standard form just from a drawing, and you can write it in component form by thinking about how far that initial point is from 0 and basically moving your terminal point to match. Now, so similarly, when we did section 12.5, we could write this as a matrix and add and subtract that way as well. Instead of thinking it through, you can use a matrix. And let's look at for other, that one we could do, the adding and subtracting ones you could do pretty easy without a matrix. But what if we wanted to rotate something? So what if we wanted to rotate this vector that is 3, comma, negative 2. And we want to rotate it by 90 degrees. So I'm going to rotate it. First of all, I'm going to write this vector as a matrix, which would go 3, negative 2. And what I'm going to do to this is multiply it by that matrix that says we can, that does the 90 degrees. Now, that matrix for the 90 degrees, excuse me, I'm going to yawn, was 0, negative 1, 1, 0. That was our 90 degrees matrix. And if we multiply it by 3 over negative 2, now our answer, it's a 2 by 2, 2 by 2, and a 2 by 1. So the insides match, so we can multiply them, and the answer would be a 2 by 1, which makes sense because I want out just the x and the y for the component form. Okay, so I'm going to go 0 times 3 is 0. Negative 1 times negative 2 is positive 2. Add 0 and 2, and I get 2. We go to the next row, column. 3 times 0, 1 is 3. 0 times anything is 0. So 0 plus 3 is 3. So 2, 3 is my component form of my matrix. So we can rotate a vector same way we did last time in the last section by making it a matrix. What if you want to add two vectors together? So what if I say vector u is negative 2, 3, and vector v is 5, negative 2. Those are our two vectors. What if I say what's the, I guess it says that in the book, absolute value of u plus v. The absolute value threw me for a minute, but what are we going to get in component form if we add these two vectors together? So what does it look like when you add two vectors? You actually can just add the x's and add the y's and you get your answer. So we can say, all right, we go negative 2 and 5. That's going to give me 3. 3 and negative 2 is going to give me 1. Now the picture of this is different than looking at just adding the numbers. So let me show you. Okay, so the first vector, if it's in standard position, is at -2, 1, 2, 3 here. And then what I want to do from this first vector, u, is I want to add to it vector 5, -2. Oops, maybe I didn't show you my drawing very good. This is u. So from here, I want to go 5, 1, 2, 3, 4, 5 is here. And then I want to go down to 1, 2. And that is how I add one vector to another, is I connect it like this. So it's a little, that's how we get the point 3, 1. So we start with the first vector that they give us, and we're going to add to it the next vector, and that gets us to that place 3, 1 that we've already thought of. So that's kind of how you add vectors. What if you're told like 3 times a vector? So what if you were told that you had 3v and just regular v? So what if you want to draw both of these and you know v is equal to 1 comma -2? Well, all I'm going to do is if I have 3v, this is v, so I can easily draw that v if I needed to draw it. And it does have quite a few ones that you draw on this homework. Well, I guess, or pick the answer on Math Excel. You should try drawing some, but okay, 1, -2 is here. So v would go from here to here. That's vector v. And then 3 times v would be equal to 3 times 1 is 3, and 3 times -2 is -6. It's like scalar multiplication. So that would put us at 3. 1, 2, 3, 2, 3, 1, 2, 3, 4, 5, 6, right? Yep. Here. Whoop, whoop. And that does look 3 times bigger, right? This one versus this one does look 3 times bigger. So there's vector v and vector 3v. You just times by 3. Okay, so then let's see. We go into talking about whether vectors are normal, and we look at their dot product, and it sounds a little more confusing than it really is. So we're looking at just whether two vectors are normal. So what is a dot product? Because we're going to use that. Dot product is just where you take, if let's say v equals v1 comma v2, so this is just vector 1, and we'll call w the next vector, and we'll say w1 comma w2. So those are just numbers on two vectors. The dot product is where you take v times w, which is equal to v1 times w1 plus v2 times w2. So that's our dot product. You times the x's times the y's, and you add your answers together. If v times w equals 0, the two vectors are normal or perpendicular to each other. So if v times w equals 0, then we're going to say they are normal. The two vectors are normal or perpendicular. And if you want to write the word perpendicular, that's fine. I did the symbol. Okay, so dot product allows us to see if something is normal. Let's look at an example of this. So what if I say t is equal to 2 comma -5 and u is equal to 7, 3. Are these normal? Yes or no? Um, so it says multiply your x's. So 2 times 7, and you want to add it to the y's, -5 times 3 being multiplied. So 2 times 7 is 14 plus -15 equals 1. So they are normal or not? Not normal. Right? Didn't equal 0. Okay? So you just, that one's not too bad. One other problem that I thought I wanted to show you, maybe I'll just not waste another piece of paper because it's only one more problem. See, you can see it through, so I usually try to just use new paper every time. I like to waste paper. Okay, so oops, this is my second one. What if you say something like C plus V equals B and C equals vector 2, 0 and B equals vector -4, 3? So you have these two vectors, and it's saying, all right, C plus what would be B? Well, there's a couple ways you can think it through logically to get there. There's a couple ways to think through it. I wrote it as a matrix, and this is how they show it in the book. C is 2, 0, plus, I don't know, this would be x over y. So we find those two numbers equals b, which is -4 over 3. It's a lot easier to look at it this way and solve the top equation and then solve the bottom equation and easily find your x and your y or your vector v. So 2 plus what would give you -4. So you'd have 2 plus what equals -4 minus the 2 over and you get -6. And the next one, 0 plus y equals 3. Well, 0 doesn't mean anything, right? So y just equals 3. And we could write this as a vector of x, y, -6, 3. So they did a couple questions like this where you have to think through the vectors. It's just simply adding and subtracting. They made it a little more confusing. But the bigger thing with these is just being able to draw them and do some of those same transformations that we did in section 12.5 with a 2-by-1 matrix, which we happen to call a vector. Okay, hopefully you found this